Hello, everyone. In this video, we will see the interaction between computer science and nanotechnology by highlighting two parallel axes. The first axis includes the use of nanotechnology in enhancing computer systems and devices, and the other one includes the role of computer science in promoting nanotechnology. Nanotechnology, the science of manipulating matter at the atomic and molecular scale, has unlocked a myriad of possibilities for computer science. Nanoparticles and nanostructured materials exhibit markedly different characteristics than their visible scale counterparts. For example, gold nanoparticles seem red rather than shiny yellow, while aluminium, which is stable at the macroscale, turns flammable at the nanoscale. The distinct and unforeseen differences in attributes between the nanoscale and macroscale are owing to the dominance of quantum confinement and high surface area phenomena at the nanoscale. As material dimension shrinkages to the nanoscale, the fraction of atoms on the surface grows considerably. This results in an escalation in the surface area to volume ratio. The augmented surface area to volume ratio, among other things, modifies the material's reaction, mechanical, thermal, and catalytic properties. 10. Researchers believe that Richard Feynman's archival talk, "There's Plenty of Room at the Bottom," 63 years ago, is considered the starting point and scientific glimpse of nanotechnology. The application of nanotechnology in computer science started with the miniaturization of semiconductor components. Moore's law, designed by Gordon Moore in 1965, states that the amount of transistors on a chip is twofold every 2 years. Moore's law was applied for a long time. However, Moore's law became inapplicable for the next years. Silicon transistors have reached their physical limit for optimization, and the size is approximately frozen at 5 nanometers. Within this size, electrons jump nearby and turn up in undesirable places. Inside this tiny space, it turns out to be difficult to organize the fine structure of the silicon wafer, which is crucial to control the electrical properties. An additional factor that gradually ended Moore's law is the rising costs, since building extremely tiny materials, billions at a time, necessitates novel and enormously pricey apparatus. So, how nanomaterials affected the semiconductor industry is that nanomaterials have become an attractive alternative for manufacturing the next generation of transistors due to their superior electrical characteristics, responsiveness, capacity to interface with other systems, high stability, including thermal stability, and naturally tiny size. Generally, there are binary main attitudes for synthesizing nanomaterials, bottom-up and top-down. In the bottom-up approach, the nanomaterials can be synthesized through the chemical reactions among the atoms, or ions or molecules, while top-down approach comprises the mechanical procedures to crush or break the bulk materials into numerous parts to form nanomaterials. In addition, the bottom-up nanofabrication techniques accessible today enable the creation and integration of a large number of these tiny transistors onto chips and circuit boards. Nanomaterials have been utilized to make a variety of different kinds of transistors. The field effect transistor, FET, transistor, for instance, is often encountered due to its adaptability and compatibility with devices that have initiated to include of nanomaterials into their fundamental design. Circuit boards are a prime example, and the size of nanomaterial-based transistors plays a crucial role in this regard. Transistors are significantly used on circuit boards and processing components inside computers to convert and strengthen electronic signals. The more transistors per unit area on a processor chip, the quicker it runs, resulting in an improvement in total speed and processing capability. The ability to fabricate nanotransistors allows integration of more transistors per space, thus enhancing chip performance, particularly with using highly conductive nanomaterials. For instance, carbon nanotubes, CNTs. Since carbon nanotubes can be synthesized atom by atom, they may be incorporated into chips in a customized manner that is consistent with the chip's standard design and the various components inside a device. Next, nanotechnology and quantum computer processor building. IBM has made a significant advancement in semiconductor design and manufacturing with the announcement of the first chip in the world using 2-nanometer nanosheet technology. Researchers have demonstrated a novel nanophotonic equivalent processor accomplished of resolving partial differential equations. When electrons are stimulated, quantum dots emit just one wavelength of light. It is a novel material synthesized by the bottom-up process of nanofabrication. They have the potential to revolutionize computer science and quantum information science by enabling the structure of a scalable, cost-effective, and fault-tolerant working machine. Quantum dot technology has some promising applications in this area.
In the upcoming years, quantum dots may be utilized as quantum bits and to form the foundation of quantum computers, in which the twofold rate of traditional computers is reproduced by quantum bits or
Qubits, which may be in any state, run between 0 and 1 concurrently, both 0 and 1. Due to the quantum computer's ability to handle several circumstances concurrently, it is believed that it can conduct 1,000,000 calculations with one accord. This would significantly increase the computer's speed.
the growth of quantum computers until now in its infancy. Meanwhile, quantum computers that rely on quantum mechanical phenomena are at risk and faces several issues such as noise, coherence loss, and quantum bit loss.
The applications don't stop here. There are still plenty of applications of nanotechnology in computer science that extend far beyond these. As researchers delve deeper into the realm of nanoscale manipulation, new possibilities emerge for revolutionizing computing technology. Nano-memory devices represent another significant application of nanotechnology. These devices leverage nanoscale materials and structures to store and retrieve data, offering the potential for higher storage density, faster read/write speeds, and lower power consumption compared to traditional memory technologies. NanoRAM is a proprietary computer memory technology from the company Nantero. It is a type of non-volatile random access memory based on the position of carbon nanotubes deposited on a chip-like substrate. DNA computing is another exciting frontier where nanotechnology intersects with computer science. By harnessing the unique properties of DNA molecules, researchers are exploring the potential for using DNA as a computational substrate. DNA computing holds promise for solving complex problems in areas such as cryptography, optimization, and bioinformatics. Next, the concept of using nanobots to repair DNA illustrates the convergence of nanotechnology with biotechnology and computer science. These nanoscale robots could be programmed to target specific DNA sequences, enabling precise repair of genetic mutations and potentially revolutionizing healthcare and medicine. Nanomaterials have been utilized to generate a range of modules within fiber optic cables.
These comprise optical filters and Bragg gratings, which are either utilized on their own within fiber optic
cables or to construct other modules, for instance, fiber optic anemometers. Nanotechnology has inspired new directions for fiber optics research, including fiber optic nanophotonics. Numerous nanomaterials are utilized to construct diverse parts of fiber optic cables since they interact strongly with the propagating light. Other areas where nanomaterials are utilized to create photonics-based devices include fiber optic rectennas to change electromagnetic waves into an electric current, more advanced magnetic recording devices, and ways of refining the light intensity in spectroscopy and solar cell technologies, to name a few. Okay, guys. Now, we are going to see the contribution of computer science and nanotechnology in terms of computer simulation, nano-image analysis enhancement, and the usage of artificial intelligence in nanotechnology.
Meanwhile, investigational study at the nanoscale is very pricey and
technologically challenging. Researchers are urged to utilize computational approaches to simulate the behavior of nanostructures. Let's see what are those. Quantum ATK, written in C++ and Python programming languages, can be used to explore the nanostructures of particles from the atomic level.
It enables concurrent execution of fundamental
operations and resumption. Ascalaf Designer, written in C++, can be used for molecular model building such as polymers, nanotubes, proteins, nucleic acids. It also provides interaction with the quantum mechanical programs. Avogadro software, written in C++, can be used to fix or ignore a specific selection of atoms in a molecule, as well as to fix distances and angles. Avogadro offers a semantic chemical builder and platform for visualization and analysis. Nanotube Modeler, written in C++, used in the creation of nanotubes, nanocones, buckyball, graphene sheet, etc. Nanotube Modeler gives the users possibility of hiding or showing the atoms and bonds from the working environment. So that's all, guys. There are still plenty of things that need to be included in this video, but due to the time constraint, I am ending it here. You know, the development never ends here. As long as we continue to delve deeper into the applications, it never ends. This relationship between nanotech and computer science will lead us to the future of computing, as well as the improvement of analyzing nanoparticles in a greater factor. See you later.